Hi everyone and welcome back. In this video, I want to continue our discussion from last video, introducing recursion. So let's just recap by saying, what is a recursive function? So a recursive function is a function that directly or indirectly calls itself. So we wrote this recursive countdown function and it directly called itself, and that's why it's a recursive function. So right here on line 26, recursive countdown passing in n-1, this is our recursive call. You can see that in the body of recursive countdown, we are calling recursive countdown. Also recall that there are two elements of recursion. One is the base case, which is when we stop recursing. Here was our base case for our countdown. So the base case with recursion is like the Boolean condition for loops, where once the Boolean condition is false, you stop looping, you stop iterating. The second element of recursion is code to approach the base case. So right here, line 26, this is our code to approach the base case, where we're passing in n-1, which is one step closer to the base case. This is like the progress towards the Boolean condition being false, like the I++ or the I-, or the cur node gets cur node next with our loops, right? Eventually we want to stop looping, eventually we want to stop recursing, and that's what our recursive step, our code to approach the base case, can do for us. All right. So I want to take a few more notes here, and then we're going to see more examples of recursive functions. Specifically, we're going to look at three mathematical functions that return values so that we can see how values can be kind of propagated up the call stack in order to return a value to the originating call. All right, so what would be a few pros of recursion? Well, we can have simple, short, and elegant solutions to some problems where the iterative solution could be very long and very clunky. So I'm going to write compared to iterative solutions. Okay, this isn't always the case, but for some problems, this really is the case. Another pro is it's commonly used by other programmers. So in order to read their code, contribute to their code, communicate with them about their code, we want to know how to use recursive functions in recursion. All right, and then the major con, I would really say there's one con, which is there's a high memory overhead. I talked about this towards the end of the intro video, just briefly, but I want to mention it again here and get it down in writing in the code because it's so important. So there's a high memory overhead. Recall that call stack diagram I drew where every recursive call is a fresh copy of the function working on a smaller subproblem of the original problem, right? So that involves the call stack and the stack region of memory where there has to be local variables declared for all of the variables in that fresh copy of the function. So definitely a high memory overhead, and I'm going to write again, compared to iterative solutions. So keep that in mind. It's not always going to be the most efficient solution. In fact, most of the time, it's not going to be the most efficient solution, but most of the time, it is going to be the more elegant solution, depending on the problem. All right, so let's take a look at the code that we're going to go through today. We're going to go through three examples. We're going to first start with writing a function that multiplies two numbers together using repeated addition. We're going to solve this iteratively and then recursively. That way you can see the two different solutions. All right, let's start with an iterative solution. So we're going to have 2 times 3. We're not going to use the multiplication operator. We're going to instead use repeated addition. So 2 times 3 is 2 added 3 times. 2 plus 2 is 6, which is 2 times 3. All right, so let's code this up. To save a little bit of time in this video, I already went ahead and stubbed out these functions that we're going to write today. All right, so iterative multiplication, we'll pass in 2 and 3, 2 times 3. All right, so here's what we're going to keep track of. We're going to have to keep track of the sum, right, because we're going to do repeated addition. And we're going to have to keep track of a loop control variable, I. So we're going to start I at 0, and we're going to take I all the way up to n, stopping at n so that the loop repeats n times, which in this case will be 3 times. And each iteration of this loop, we're simply going to accumulate in sum m. So this is going to be like adding 2 from our call here in main, right? We're going to add 2 3 times. We're going to add m n times. And then all we have to do here is return the sum. These are a bunch of warnings because I have all these stubs that don't return any values, but we have no errors, so it's compiling. All right, so let's print out this result so that we can see it. All right, we see 6, looks good. All right, now let's do this recursively. So we just solved multiplication using repeated addition iteratively. Now let's solve it recursively. All right, so remember, we have to think about what is going to be our base case. Okay, what is going to be our base case? So if n is equal to 1, then we're simply going to return m, right? If this is the last time we need to add m, then we will return m. Otherwise, we need to have our recursive step, which is going to be returning m plus recursive multiplication, passing in m still, but n minus 1, because we just added 1 copy of m to our result. And that's it. That's our recursive multiplication. And there we see 6. Okay, so the key here is because recursive multiplication returns an integer, our return statements are going to have to return an integer. So when n is 1, that's the last time we need to add m. Okay, so I'm just going to return m, which will be replacing this call right here with its return value, and we'll add m to m, which will give us 2 plus 2 is 4, and then we'll return that, which will replace this call with 4. We'll add 4 to m, 4 plus 2 is 6, we'll return 6, and that will get us back out to our originating call. All right, let's draw that so that it's more clear. All right, so let's start with our first call. So we have, I'm just going to call it multiply to be simple. That way I don't have to write out recursive multiplication each time. All right, so we have multiply to 3. This is our originating call from main. Okay. What we're going to do is pass in m again, which is going to be 2, and then we're going to pass in n is 2, right? Because we're going to be subtracting 1 from n to our second call. So now we have multiply to 2. Okay, now we're going to pass in to our third call. M is still 2, we're not going to change that, but n is going to be 1. So this will be multiply to 1. Okay, now we've reached our base case, right? We've reached our base case where n is 1. Okay, so we've reached our base case. So now what we're going to do is we're going to return m, which is 2. Okay, so we're going to return m is 2, back up to this call right here. And so what this is going to do is it's going to return m equals 2 plus 2, which is this 2 right here. So this is going to return 4. So now we're up at our originating call up here, and we're going to return m equals 2 plus 4, which is 6. So 6 is what our final result is, which is what gets sent back to main. All right, so the red, okay, is what value is going to be returned to what originating call, which is going to be our recursive call number 1, our second call overall. And then the green is what's going to be returned to our originating call, which is our call number 1, right up here. And then blue is what's going to be returned to the originating call from main. All right, let's move on to our next function. All right, so our next function is write a function that raises a number to a power, or said another way, raising a base to an exponent. So for example, 2 to the 3 is 2 times 2 times 2, which is 8. Okay, so this is going to be really similar to our last problem, but instead of repeated addition, we're going to do repeated multiplication. All right, so let's solve this first iteratively and then solve it again recursively. All right, so here we're going to have a product, but we're going to initialize the product to 1, not to 0, because 0 times anything is always 0. And we will still have our loop control variable I. So I is going to be 0, I less than our exponent, which is our second argument, I plus plus. Okay, we're simply going to accumulate the multiplication of product and our value of base, and then we'll return our product. Okay, so let's do an example call for iterative power. So for this, let's do 2 and 3 again, which was the example, which should be 8. And there we see 8. So let me just trace this for you. So 2 is coming in as our base and 3 is coming in as our exponent. Okay, so we're going to run this loop exponent number of times, 3 times. Each time we're going to multiply product by 2 and then store that result in product. So the first product is 1, so 1 times 2 is 2, store 2. Next iteration, 2 times 2 is 4, store 4. Next iteration, 4 times 2 is 8, store 8. Okay, this is going to be false, and then we'll break out of the loop and we'll return 8. All right, great. Let's solve this again, this time using recursion. So remember, we start off with what is our base case? So our base case is if exponent is 1. If exponent is 1, what do we want to do? We want to return our base, okay? Our recursive step is going to be calling recursive power again, multiplying its result by base and returning that result. Okay, we want to emphasize that base is always going to be the same. We're always going to be multiplying by, in this case, 2. And then our exponent, we want to subtract 1 from so that we have that progress towards our base case. All right, that's it. That's our recursive power solution. So we're going to get all the way down to our base case, which is 1. And then we're going to return our base, which is 2 in this call. So 2 will replace this value right here. We'll multiply 2 times base, which is 2. 2 times 2 is 4. We'll return 4. And then on the previous call, 4 will replace this function call as its return value and multiply 4 by base, which is 2. So 4 times 2 is 8. And then we will return 8, which is going to be the value returned to the originating call right here. And there we see 8. All right, looks good. We won't draw a call stack diagram for this one, but we will for our last one. So our last one is going to be an iterative and a recursive factorial. Okay, so write a function that evaluates the factorial of a number. So a factorial of a number is starting with that number times that number minus 1 times that number minus 2, so on and so forth. So for example, 3 factorial is 3 times 2 times 1, which is 6. Another example could be 5 factorial, which would be 5 times 4 times 3 times 2 times 1. So 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is 120. So we can use those test cases if we want. All right, so we're going to start again with an iterative solution. So let's pass in 3. And while I'm here, let's also pass in 5 and make sure that it's 120. All right, so for our iterative factorial, it's actually going to look really similar to our power. We're just not going to be multiplying always by the base. We're going to be multiplying by I, our loop control variable, that is going to start at n and go down to 1. All right, so let's do int result is 1 and I is 1 as well. All right, so for I gets 1, I less than or equal to n, I plus plus, or I could go the opposite. I is assigned n, I greater than or equal to 1, I minus minus. So result times assign I, and then I'm going to return result. And there we see 6 for 3 factorial, 3 times 2 times 1, and then we see 120 for 5 factorial, 5 times 4 times 3 times 2 times 1. All right, let's do our recursive factorial. So I'm going to just use those same 2 test values here. All right, so remember, whenever we start thinking about a recursive function, we want to think about our base case. So what is our base case? Our base case is going to be if n is equal to 1, right? So n is going to start with a high value. We'll subtract 1 for each one of our recursive calls, and once n is 1, then we know how to solve the factorial of 1, right? So 1 factorial is 1. So we're simply going to return 1. Okay, now our recursive step, how are we going to get from n equal to, say, 3 or 5 all the way down to 1? Well, we're going to subtract 1 for each one of our recursive calls. So what are we going to do? We're going to return the current value of n times whatever the factorial of n minus 1 is. All right, that's it. Let's try it out. All of our warnings are gone, and we're getting 6 and 120 as well. So in order to make our iterative solution look more like our recursive solution, if I wanted to, I could start I at n and then do I greater than or equal to 1, I minus minus, and I would get the same result. All right, let's draw a call stack diagram for our factorial, just to help it make a little bit more sense what's going on. All right, so our originating call is going to come from main. I'll just call this factorial. So let's do the case where we pass in 3, because it'll be a little shorter. All right, so factorial of 3. We're going to test, are we at our base case? No, we are not. So we're going to have our recursive call where we pass in n is 2. Okay, for this call of factorial, n is going to be 2. We're going to test to see if we're at our base case, which is n equals 1. We are not, so we're going to do a recursive call, passing in 2 minus 1, which is 1 for n. Okay, for this call of our factorial function, we're going to have n equal to 1, which is our base case. So we've reached our base case, which means we're going to return a value. What are we going to return? Well, our base case is 1, and the factorial of 1 is 1. So we're simply going to return 1 to this call right here. So this call right here is going to return n equal to 2 times 1. Okay, so this is going to return 2. All right, and then this last call up here, this is our first call, our originating call. It is not a recursive call because it came from main. So what it's going to do is it's going to return n equal to 3 times 2. And this 2 came from the return value from its recursive call, passing in n minus 1. N is 3, 3 minus 1 is 2. That 2 right there. All right, so what is 3 times 2? It is 6. So it's going to return 6 to main. All right, so in this video, we went through 3 different mathematical functions, all very simple functions. We went through multiplication, exponentiation, and factorial and solved them 2 ways. First, iteratively, which is something that we've been able to do for a while. And then we solved them again using recursion. And we saw that the solutions using recursive functions were actually really short and really elegant, right? So there's a lot less going on, for example, in this recursive factorial than there is in this iterative factorial. They're both simple solutions, but I would argue that the recursive factorial solution is more elegant, definitely more elegant. All right, that is it. Thank you for watching.